Okay, I just wanted to do a quick video about setting up a case in runpod. So first of all, go to the runpod website and log in with username and password. Assuming you've already got some credit on the account, I've got some $10 that I put on there yesterday. So I want to run UFO LBM, my lattice Boltzmann solver. So I'm just going to go to New GPU pod because I want a GPU case, and then you've got all of these ones to choose from. Now the one I sometimes use is this A40 because it's extremely good value. It's just $0.4 an hour and it's got loads of RAM there. So you select that, go down a little bit and then deploy. Simple as that. So I've just selected one instance of that particular GPU. So it gives you some random name for this case, and it's got the connection details here of this lot, so it takes a few moments to connect. As soon as it's connected, I should be able to load JupyterLab and start uploading my case data. Okay, so that has created that. So I can see some of the details here, the amount of RAM and whatnot. Connect. So the first thing I want to do is to start JupyterLab, and it's pretty straightforward from there. So before I even open a terminal, I'm just going to upload the files that I need for that particular case. So if I go down to my working directory, this is the one. So all I need to upload to run this CFD case is the GPU executable, my text-in file, and the geometry. So those three things. So you have to be, well, let's just open those first. So you have to have a GPU executable that's been compiled for that particular GPU, which this has. And what that means is that in the compiler options, let's just quickly load. Yeah, in the compiler options, I've got, so if I'm compiling my solver for different platforms, so if I'm just running it in serial, it's ACC equals host. If I want multi-processor, then it's ACC multi-core. If I want GPU, then you have to specify the GPU, so I've specified CC86 for this A40. If I was using the slightly less capable T4 GPU, then we use CC75. Sometimes they use GPU CC all, which in theory does it for all GPUs. But when I tried that one on this particular runpod A40, it didn't work. So I had to specifically put in the CC86. And I've also got a G-Fortran compiler, which is quite useful for picking up errors. So sometimes when I'm compiling, I would run this one first to see if there's any errors or anything that needs sorting out. But the compiler options for the NVIDIA compiler are sort of less useful. So having uploaded those files, I can run it. It really is as simple as that. So this is my working directory. I've got my geometry, got my executable, I've got the input file. The only thing I need to do is to make the executable like that. That's now executable and I can run it. Let's just take a quick look at the settings in here. Yeah, so this is the geometry file, VTK format, cell size. I'm just checking some of these. This is the domain size, symmetry boundaries, number of saves and iteration details for VTK slices. I just want to save the K slices, I think, at this stage. Reynolds number, reference length, speed. So that all looks okay. So I can start that running, and as soon as I start that running, I'll start to see something going on here with these dials, but it hasn't really started using the GPU yet. Utilization 14%, CPU. When it starts running and it's just marking the cut cells, it's running in serial, so that's going to be quite slow. So anyway, that is a very quick demonstration of how easy it is to upload CFD case to runpod and then start it running. And once that actually finished marking the cut cells, then it will start running in parallel. But what happens then is that you will start seeing some output files appearing here. So every 1,000 iterations, it's going to write a VTK file. And so as soon as it starts running, you can literally download one of those files and then look at it. So you can kind of check how it's running, if the solution looks like it's running properly. And what I'm doing here is I'm rerunning this case with an atmospheric boundary layer profile, because the previous runs that I've done for this Niigata test case, I've just had like a constant inflow boundary. But then I've coded in a boundary layer profile. I ran it yesterday and I made a mistake, so it wasn't working properly because I coded it wrong. So I'm just rerunning it with an inlet boundary layer profile based on the power law. You can use the 7th power law for velocity boundary layer profile. And so I've just coded that in. I'm going to rerun it and then see how it improves the results, which hopefully it will show a good improvement in the results. So looking at this, it's still not really got going yet. It's not got to the parallel part of the code. So it's finished the cut cell. It's going to start running soon. So this is showing the flood fill operation. This shows how many cells. So we've got just over 120 million. 120 million cells for this domain. And it started iterating now. So you can see every output is 10 iterations. So it's running quite fast. So I think it takes sort of a minute or a minute and a half to between the output, writing the output files. So if we go back to this one, then we can see what's going on here. So it's showing here that its system memory is 16.5 gigabytes, and oh, there we go. GPU utilization's gone up to 100% now, and system memory 16.5. VRAM utilization 89%. That's at 16.5 gigabytes. That's interesting. That says 89%. Is that at 34%? It's a bit confusing. Anyway, that's continued to run now, and so I'm going to leave that for 3 hours. That's going to take 3 hours to finish running that approximately, and so I'll come back to it a bit later when we've got our result.